welcome everyone, and thanks for the invitation for the talk. As he said, the title is what we talk about when we talk about distributed systems. You know, it's a play on words, and it seems it's not the appropriate title for websites that are non-responsive, because in the website only says about distributed systems, so I need to cut the thing short, maybe. So, about me, I was born in the third world, in Uruguay. I moved to the second world like 7 years ago to China. And 4 years ago, I moved to the first world, Switzerland, where I live now, which is actually the third world by the original three worlds theory. And in the third world of Switzerland, I work as a RabbitMQ core developer. I don't know how many of you have heard about RabbitMQ? Okay, everybody, mostly, cool. Yeah, and today I'm trying to talk about the distributed systems. And the idea is to give like an intro to the topic, because I had this problem, or I'm kind of having this problem today now, trying to learn about distributed systems. What is it? That there is so many things to read. There are so many papers, so many books that it's quite hard to actually understand where one can start. And even when you find a book that seems appropriate, actually, it has nothing to do with what you were trying to do, to solve, for example. So this talk, you are not going to leave this place being able to implement Paxos. Maybe you are super smart, and you are going to do that, but that's not the goal of the talk. The goal of the talk is that at the end, we are able to say, yeah, this paper is relevant to my current work, or this book, or whatever. So the almost canonical definition of distributed systems is from Leslie Lamport, which says a distributed system is one in which the failure of a computer you did not know existed can render your own computer unusable. In Spanish or in French, that means when Facebook doesn't work, the whole internet doesn't work. And as a user of Facebook, you have no idea why things are not working, basically. And in developer English, we had a distributed Git thing, but we made it centralized. So when Git doesn't work, nothing else works anymore, basically. But to be a bit more serious, in distributed systems, there's a lot of jargon. And as you know, jargon is all these special words or expressions that are used by a particular profession or group and are difficult for others to understand. And that, for me, is a key problem of the literature around distributed systems. So one definition, which is actually by a French researcher, Michael or Michel right now. He's from INRIA, I think. Says that in a distributed system, you have many entities trying to solve a problem, like nodes, processes, and so on. They have partial knowledge of what each other knows. And there is a lot of uncertainty. You really have no idea what's going on around on all these computers unless you start asking. But here, the absolute knowledge from philosophy, we see it in practice that is totally not possible. Of course, probably the laws of physics show us that we cannot know something immediately because light needs to travel in space and blah, blah, blah. But this, at some point, applies in distributed systems because computers, to share this state and their knowledge, they need to communicate. So even if a computer tells you, I think some fact is this or that, at that very moment when you learn that, the computer might be thinking the opposite because you have no idea about that. And as I said, it's a very deep rabbit hole to get into this. For example, we want to maybe know what to read, which papers, for example. So I'm not sure if you can read that. You don't need to read it anyway. One famous paper is called Impossibility of Distributed Consensus with One Faulty Process. Another one is the Part-Time Parliament, which is basically the paper that introduced Paxos. time clocks and the ordering of events in a distributed system. That's the seminal paper that founded the distributed system as a science, let's say, or as a field in computer science. There's a simple totally ordered broadcast protocol. This is from Yahoo when they introduced ZAB, the protocol used by Zookeeper, consensus library, something like that. And recently, Diego Ongaro, he, with another collaborator, they wrote In Search of an Understandable Consensus Algorithm. Basically, that's the Raft paper that everybody says Paxos is really hard to implement. Raft should be easier. By the way, do you know what have you heard about these things already, or is this all completely new to you? Okay. It's fine if you have no idea what it is, because that's the point. That when you go to these things in search of or impossibility of distributed consensus with one faulty process, what even that means? What is consensus? What does it mean to be an impossibility? What is a faulty process? It's not what you think, and so on. There is so many things in this literature. Which books? There are a lot of books. That's from my library. I didn't pay for all of them. Luckily, my company sponsors some of them. But still, there are a lot of books. Some are really great, some are great, but they are not what you're looking for. So it's quite a mess to get into this. Then there is the why. Maybe you're here because you're curious, because you are already doing distributed system research or programming, and you want to know a bit more, or see what this guy has to say, whatever. But at the end of the day, we don't have infinite time to be reading all those papers, reading those books, seeing what we can implement, what not. And I think there is a need for a guide that tell us, yes, this book or this paper will help you solve your problem or not. So the problem with learning. In distributed systems, there are different models. So you can buy a book which has nothing to do with what you want to learn, even though the title of the book says so. For example, if you want to see them later, I have them in my bag. That's why I brought a bag. One is called Programming Distributed Systems. There's nothing in that book about programming distributed systems. It's just about different formalisms from academia on distributed systems. So why do I care? In models, when algorithms for distributed systems are described, they use a timing model, which is the timing assumptions made on the distributed system we are trying to implement are asynchronous or synchronous. And they have a very specific definition also. It's not asynchronous Node.js, synchronous Ruby. No, it's not as simple as that. Then they analyze the interprocess communication used by all these collaborating peers that are trying to solve a problem together. For example, if you have multiple databases, they are all trying to commit one record to the file system. That's the problem they're trying to solve together. Now you trying to be really smart, you went to the ATM around the corner and you send your brother to the ATM in the other side with a copy of your card, and you try both at the same time to take money. The distributed system, these peers, they need to... I think here I covered this, but whatever. Anyway, the thing they're trying to solve in this case is to make sure you don't steal money from the bank when you take money from the ATM, basically. So to do that, they have to exchange information some way. Failure modes. This is really important. What it means for a process to be on a failure state and up to what level that process can do one thing or the other. We will see soon. So on the timing model, synchronous model, you have like a finite state machine or whatever that is executing steps. In the synchronous model, we know exactly how long each step takes. No more, no less. You know, to go through one step of the algorithm, it will take, let's say, 1 millisecond. And it will always be like that. When, for example, this synchronous model is sharing information, this model knows how long it takes for a message to go from computer A to computer B, exactly. And it knows how long it takes for the other process on the other end of the network to say, I received this message. That is one step that is being executed. And then if the other process by the algorithm has to reply to you, then you know how long it will take the message to arrive back to you. That's on the synchronous model. The async model, this is the living la vida loca version, basically. There is no assumptions of time. There is no assumption of how long messages go on the network. So in this model, for example, you have no idea if a process crashed completely or is just being very slow to reply. You are on WhatsApp talking with your boyfriend or girlfriend or your significant other. WhatsApp is showing you seen, and you're going crazy there why they don't reply to you, and that's the synchronous model. Is the other guy dead or person? Is the other person dead or they just don't want to reply? I don't know. A synchronous model, kind of like that. And then a more realistic one is the semi-synchronous model, when there are some limits, some constraint imposed in the system. Because on the synchronous one, it's a very perfect world where we can implement things and do. I mean, for example, in that model, you can immediately tell if a process has crashed, because you know how long it takes for the message to go, you know how long it takes to receive the message and to reply to you. If after that time you don't receive a response in that model, in the synchronous model, it's for sure the other process is crashed or faulty or something. In the asynchronous, we have no such luxury. And at the same time, it might never reply back to us, so it's not so useful also to have an algorithm that we have no idea if it will terminate ever. That's why they have also this other mixed model. So I have books there that they will teach you how to implement consensus algorithms for the synchronous model. Cool story, bro. For RabbitMQ, that's totally unacceptable because network partitions will happen. We have no idea if the node on the other side is alive or not, so synchronous model is not useful. When I bought that book, I had no idea that that synchronous word in the title has that very specific meaning. Maybe I'm a bit dumb too, I don't know. But yeah. Then there is the interprocess communication. This is quite easy to understand, is if they're using message passing or shared memory. If you know, like Erlang, for example, you have processes running on one virtual machine, and they are all exchanging information by sending messages. I will say that most of the modern literature on distributed systems is around message passing. Shared memory, I haven't seen so many things, but it's there still. They have a memory where they use that to communicate, basically. And then failure modes. This is also very important, and we will see soon. When a process fails, it can be, for example, in a crash stop failure mode. It means it crashed, it never came back again. So if you have an algorithm that accepts peers coming back into the network, it's not that model, for example. That's crash recovery. A process can come back alive and keep trying to solve this distributed algorithm. Then there is the omission fault. In this case, the process can either crash stop, can do crash recovery, or it can omit messages. It can omit from receiving messages, from sending messages, or both. So in that model, sometimes messages might not be received by the other peer, or it might not reply. For example, if the process is failing to reply, but is able to always receive messages, is doing omission of replies only, we know that that process at least has the current state of the system. It may not have replied further with what it did, but at least it knows all these transactions happen in the system, for example. So there are some small differences between the different kinds of omissions. And then there is the arbitrary failure mode, or Byzantine, which a process can do basically whatever it wants. It can do any of those. It can lie on behalf of a peer on the system. Basically, I don't know if you played the telephone game, something like that. It's like I ask process A, how many rows you have on the database? 2,000. Then some of you ask me, how many rows are in the database? I tell you 3,000. But the other peer just told you there are 2,000. Yeah, but I'm saying 3,000. And you can say, like, who is going to do something like that? If somebody is able to hack into your system, they can impersonate a process in the system, and they can like start doing all these kind of misbehaviors to the system. Or even, they can even give always correct answers and write the wrong thing to the file system, for example. There can be many things in the last one. It's the hardest one to solve, but if you solve a problem for Byzantine failures, you solve for the other ones. That's the key of this model. So, I need to go back, sorry. Algorithms, then there will be with some timing model assumptions, with some IPC assumptions, and with some failure modes assumptions. Based on that is what they will help you to solve or not. As we will see later, that doesn't mean that an algorithm for the synchronous model is completely useless. They are useful sometimes in showing that if a problem cannot be solved in the synchronous model, then it cannot be solved in the others, because in the synchronous model, there are way too many restrictions. So we will see later what that means. Sorry. Then there is these other conditions of algorithms, which is the liveness and safety properties of algorithms. This paper is kind of seminal on that topic. And safety basically says some bad thing does not happen during execution. What is this bad thing? If an algorithm may assume that the communication link will not invent messages out of thin air. On WhatsApp, for example, you expect that, I don't know, if you tell your wife, I love you, on the other end doesn't say, I hate you. I mean, stuff like that. An algorithm will tell you, we assume that links do not invent messages out of thin air. That will be a requirement of the algorithm, will be a safety property of the algorithm, to name an example. Liveness is good things happen during the execution. So the safety is bad things don't happen. This one, at least at some point, something good will happen. This is the hope thing. For example, with the communication example, a destination process eventually delivers the message. It's like WhatsApp is telling you, we may take 2 years, but at some point, you will get the message. Like the Tom Hanks movie when he goes with the FedEx package, I don't know how many years after. At some point, he did it. So that's the liveness property of this FedEx algorithm, let's say. So taking this into account, let's try to see this paper. It's called FLP in the literature because the authors are Fisher, Lynch, and Patterson. It's not called FLP1. One is a index down there, a reference. So this algorithm is actually, this paper is called Impossibility of Distributed Consensus with One Faulty Process. And the idea, as the abstract is saying, the consensus problem involves an asynchronous system of processes, some of which may be unreachable. The problem is for the reliable processes to agree on a binary value. We show that every protocol for this problem has the possibility of non-termination, even with just one faulty process. The thing is, they are trying to agree on a value which can be 0 or 1. What process or problem can be this? If you are trying to do distributed transaction on a database. The database needs to know if this value has to be committed to hard drive or not. All the servers need to agree on that thing. That's the consensus problem. In this case, it's on an asynchronous system, so there are no assumptions about time. And what they are saying, if one process crashes, there is no solution, basically. The algorithm has the possibility of non-termination. In this paper, we show the surprising result that no completely asynchronous consensus protocol can tolerate even a single unannounced process death. We do not consider Byzantine failures, and we assume that the message system is reliable. It delivers all messages correctly and exactly once. Again, assumptions, assumptions, assumptions. You know, it's an asynchronous system is not Byzantine. There are only crash failures. There are no omissions because the message system is reliable. All the messages arrive. All the messages are delivered. And they are delivered exactly once. So that's what they are trying to prove here. Nevertheless, even with these assumptions, the stopping of a single process at an inopportune time can cause any distributed commit protocol to fail to reach agreement. Thus, this important problem has no robust solution without further assumptions about the computing environment or still greater restrictions on the kind of failures to be tolerated. What does it mean? Why do I care? If tomorrow you need to invent your own database, because it's cool to have your own database in Hacker News or whatever, be aware that you will not be able to solve this problem. You will try, you will give your head against a wall and blah, blah, blah. It's proven that it's not solvable under these constraints. That's what's so good also about the distributed system community. It's really, I find it more a science than any other area of computer science. Because there are all these results, all these theorems. If today I come with a new algorithm for consensus or whatever, people will tell me, what with FLP, what with Raft, what with Paxos, what with blah, 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 because there is a respect for what happened before in the literature, in the research community. On the other hand, if you look at Hacker News, for example, we see a reinvention of the wheel all the time of solutions that were invented, I don't know, 20 years ago or whatever. Again, crucial to our proof is that processing completely asynchronous. That is, we make no assumption about the relative speed of process, nor about the delay time in delivering a message. We assume that processes do not have access to synchronized clocks, so algorithms based on timeouts, for example, cannot be used. And keeps going. But the point is, why I'm showing you all this boring stuff, that I believe once we know all the models that I was talking before, we know what this means. It even applies to us. If you have a system, like in real-time system, where you can know the exact time of things, this doesn't apply, for example. Keeps talking about all the assumptions that they have and so on. I don't want to bore you with that. So, what is consensus? The consensus problem is a paradigm of agreement problem. Consensus is about agreeing about something in distributed systems, and it's a paradigm. It's not just one algorithm or one solution or something. There are actually many algorithms that try to solve consensus. Paxos is one, Raft is another one. You have use-time replication, there is virtual synchrony, there are many of these algorithms. By the way, if you search about virtual synchrony, you will maybe enter the NSA most wanted list, because the guy that created virtual synchrony in the 80s, 1986 or something like that, called it ISIS. So this protocol to reach agreement and to finding leaders is called ISIS. So today, if you search for that protocol, you find more about the terrorists than about the distributed systems. Properties of consensus. If you implement consensus, you need to have termination. Every correct process eventually decides on some value. You know when you go camping and you want to come here, and there's always a friend that says, I don't care. That guy is violating this property. All the correct processes at some point need to reach agreement. Validity. This means if a process decides V, then V was proposed by some process. In the FIFA, if they propose Blatter or the other guy, one of those two guys have to be the one chosen. You cannot choose Platini, for example. Agreement. No two correct processes decide differently. When a consensus system reaches a solution, all these properties need to be reached. And in the one called uniform consensus, it means that agreement, not two processes, correct or not, decide differently. That's the only detail there. When do we need consensus? When a set of processes have to agree to take a common action. For example, atomic broadcast, I already mentioned, and group membership. When you have like a cluster of databases or RabbitMQ instances or whatever, and a new member joins the cluster, they need to, all of them together agree that that member is part of the group now, or some member left the group. If one part of the system thinks that we have 5 nodes in the cluster and the other part thinks there are 3, there is a problem. Something here around consensus is broken, basically. And more importantly, the FLP theorem or impossibility result is saying that with one faulty process in the crash top model, blah, 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 you cannot reach consensus. This means you cannot reach atomic broadcast or you cannot reach group membership. Why this is important? Tomorrow you will try to create your own library for doing these kind of things. And if you forget the FLP result, you may try with no success to solve group membership or atomic broadcast. For example, in RabbitMQ, we need to, whenever you consume a message and you mark this message as done, every process in that cluster holding that particular replicated queue needs to receive that message that the atomic broadcast, that this message was acknowledged by the client, for example. So you don't get duplicates. So atomic broadcast in the distributed system means correct processes deliver the same set of messages in the same order. So FLP tells us that if consensus cannot be achieved, then atomic broadcast or group membership cannot be achieved either. The thing is, we pack our bags and go. There's nothing to see here. I mean, we cannot achieve consensus. Processes will fail. You know, computer crashes all the time. So what do we do? There is a very good paper called Stumbling Over Consensus Research, Misunderstanding and Issues by Marcos Aguilera. He used to be from Microsoft, and I'm not sure where he's working now. In this paper, he discusses many papers of the distributed system, and about FLP, it says it's an impossibility result, but not in the sense of the halting problem of computing science, like to know if an algorithm will halt or not. It's an impossibility result under those constraints, and specifically if you have a very unfair scheduler, like processes are always scaled for later, for later, for later, and they cannot never read a message from the network or reply to a message, stuff like that. With those assumptions, then yeah, we can go home and quit our careers. But in reality, that's not the case. So there is still hope for distributed systems. They came up with this concept of failure detectors. This is a paper, the seminal paper on failure detectors, unreliable failure detectors for reliable distributed systems. And they have all description of what a failure detector is and what not. Basically, a failure detector will tell you with some sort of confidence that a process is dead or not. It's quite hard to answer that question, actually. That's why there are many degrees and classes of failure detectors. It's an external process to your algorithm. It will provide information about suspected processes. This is like the time of the revolution, exactly. You suspect people, and then they end on the guillotine. It's the same here. And the completeness property, which means if a process crashes, it has to be detected. And accuracy, it means correct processes are never suspected. So a perfect failure detector, if a process crashes, it will tell you that it crashed, and it will be accurate. It will never mark as crash a process that didn't crash. But in the real world, that's not possible. Why? Because is this process not replying to me, or is actually crashed? How do we know that? OK, we put a timeout of 30 seconds. In 30 seconds, I don't get a message back from this process. It's crashed. On second 31, the process replied back to me, but I already marked it as crashed. So it's not so easy to solve. It looks easy on paper or whatever. As we like to say, when you have this problem, just rub some perfect failure detector on it. It will be gone. No, it's not possible. And the algorithm for this, it is in one of these books. The module called perfect failure detector with an instance P throws an event whenever process P lowercase crashed, it will tell all the other processes that it has crashed. And the properties that it has is strong completeness. It means eventually every process that crashes is permanently detected by every correct processes, and strong accuracy. If a process P is detected by any process, then P has crashed. So a perfect failure detector, yeah, gives you these constraints. But, for example, you need links that don't drop any message. So you need perfect links. And you need a synchronous system. You need to know exactly how long it takes for them to execute a step and to reply back to you and so on. Is it useful? Yes and no. It's not in the practice, but in theory, it tells us that if you need those properties, you won't have them. So if it's the same when we have the PO on Scrum, and the PO comes to us and says, we need 100% unit tests. Cool story, bro. You can sell it to the client, but it's not, I believe it's not doable. And in this sense, it is the same. I will be really happy when a PO or a client can come and say, I need a perfect failure detector, because they know the literature, but they didn't understand it very well, I think. Anyway. That's why there are eventually accurate failure detectors. They have a strong completeness property that eventually every process that crashes will be permanently suspected by every correct processes. And it's a weak accuracy, which means that there is a time after which some correct process is never suspected by the one that are still correct. So you can tell, oh, maybe this one is dead, but it can't come back to you and say, no, I'm not actually dead. Oh, OK. But it kind of tries to solve this problem. And the whole discussion implementation, there are papers out there, like that one. So we have this thing. It's interesting. Try to solve problems that are failure detectors. Then you may have heard the concept of quorums. What is a quorum? A quorum in a system with crash fault processes abstraction is any majority of processes, for example, any set of more than half processes. So if we have processes that do crash fault, not Byzantine or anything else, just crash, they crash and stop and they're gone, A quorum will be that you need the half plus 1 to be alive. So if then the half of the process crashes, at least one process knows what was decided in the previous round. That's the idea of the quorum, to have one set of process, a round is executed. In the next round, there is another set of processes. Some might have crashed, but there is an intersection in these sets where at least one process is kept alive. That's why here they need half plus 1 processes. If the F means failed, if F is less than half, processes fail by crashing, there is always at least one quorum of non-crashed processes in such systems. So quorums will always be properties that algorithms need to satisfy to be correct. If you have 5 machines and 3 of them fail, like, I don't know, call your sysadmin and arrange for a beer later and cry together in the bar, I don't know. But you don't have a quorum for having consistency in your data, something like that. That's why sometimes, in this case, systems become unavailable. You have 2 machines running, but those 2 machines cannot assure you that they know what happened in the previous round because the majority crashed. Consistency. That also has a different meaning in distributed systems. It's not what we might heard on the database literature. One of the main papers is called Linearizability, a correctness condition for concurrent objects. It's very interesting and very quite easy to follow. Where, for example, you have a concurrent FIFO queue. What does it mean that this is linearizable or consistency? What's the meaning of consistency? If you have a FIFO queue, it means first in, first out. It means you put messages in the queue, and you always take the first message that was inserted in the queue. Those are the consistency that you expect from the semantics of a FIFO queue. You expect it to behave that way. Even if there are many people consuming from that queue, you expect it to behave first in, first out. If you go to a counter in the airport in a queue, and some guy from behind you is attended first, you will be mad. That's basically, they're breaking in this access of what a queue means. So if you take a concurrent FIFO queue, they will analyze linearizability based on what you expect this to be. Or you can have a stack or whatever it is you're having. Consistency will apply to what you expect that to be. One of them is called atomic consistency or linearizability. Another condition is sequential consistency. And another one is causal consistency. So in atomic consistency, even if many processes are reading at different times, you can have a linearization of events. Even if they take like a second to occur and they are concurrent, you can still trace them in one point in time. There can be multiple histories that reach to the same result, but they have to be linearizable. You will see an example soon. Sequential consistency adds more relaxations to the system. It's like Afir in this URL has a really good blog post explaining all this. In sequential consistency, for what I understand, if you post a photo on Facebook, you want to see your picture and you want to see what you put there. Maybe your friends are not seeing that. So not everybody has the same consistent view of the system, but your actions are reflected on the system. And causal consistency, okay, I don't know I need to go or something, I don't know. Causal consistency is when, for example, if you reply to a comment on Facebook, and then I come to Facebook, I don't want to see your reply with no comment. I expect to see a causal path of things. One algorithm might implement causal consistency, another may implement atomic or depends. So I told you there are many histories. Here they are reading from an atomic registry and writing. A process PJ, the second one, writes 1, and below you have the history or the linearization of those events. Process I reads 1, it's fine. Then process J writes 2, and concurrently K writes 3, but 3 in the linearization is before 2, the write, because in the history, the first process on top, when it read 2, and the other one here, it read 2. So because of how this can be ordered, you have different histories, but they are still atomic, something like that. You can read more on that book. So I'm nearly at the end. Don't get stressed, please. Don't need to kick me. This book is from a French author, Distributed Algorithm for Message Passing Systems. And this is what I meant by what do I buy, what is the right book, and what is not the correct book. If you read just by the title, it thinks that it will teach you how to build algorithms in message passing systems. But this book considers no failures, no process crashes, nothing. It's all about the best possible case. Then you will tell me, then it's a completely useless book. No, it's not useless because it introduces the concept of consistency, of vector clocks, different kind of times in distributed system, and so on, which are really fundamental concepts. I believe if you think this book is too basic, you probably don't understand distributed systems, because it's not a basic book. It's not one to take right away to practice, but it will be a very good foundation of that. Same author, fault-tolerant agreement in synchronous message passing system is very good, but synchronous. Keep that word in mind. There will be faults and everything, but they are synchronous. This one will have communication and agreement abstraction on a synchronous distributed system, so it's the other side of the street, basically. This one is quite a huge book. It's by Lynch, the L on FLP. She is a researcher from MIT, I think, I'm not sure. And this book is divided by section, like shared memory model, message passing model, asynchronous algorithms, synchronous algorithms, semi-synchronous algorithms, and so on. That one is a very good foundational book. It's really, really good. But it's a bit old, let's say. It's still relevant, but the one by the French guy is way more modern. This one is really good, reliable and secure distributed programming. This one considers failures, considers security, which most books don't consider, like how to do authentication when you do message passing, stuff like that. It's really, really good. And this one, if you're interested in Paxos and all these kind of consensus algorithms, it has like 9 chapters that explain you why you need one kind of abstraction or the other, and it's very practice-oriented. This is the guy that wrote ISIS. So be careful if you buy this book. You may end up in jail. And this one, replication, is state-of-the-art, that says there, all about replication papers, about distributed consensus, stuff like that, really good. Finding non-paywall papers. A problem with this is that all the time the papers are behind a paywall on the ACM or somewhere. But luckily, most of the time, the authors and the universities, they have copies of the paper. So if you know the author of the paper, try to find their page on a university. Sometimes you are lucky and you find the paper. Otherwise, resort to some other internet search arts that I will not speak today. Conclusion. It's a deep rabbit hole, as you could see. There are a lot of concepts, a lot of ideas to learn about. From my point of view, it's computing science, where science is still a thing. It's really good feel in that sense that you see the science aspect, you see the mathematical aspect, and so on. It's not just people waving hands like me here and trying to convince you something is good. No, there is a proof for things. Papers are cited at the end of the paper or book or whatever. All these books I mentioned are all academical books. They will all tell you this concept comes from this paper, from that paper, and so on. It's really deep knowledge. The history of the field matters. That's also really cool. And read, read, read. There is no escape. Thanks.